I'm going to wait a minute before I pick up the homework. All right. Any questions on anything? Number 3? Okay, real quick, no office hours a week from today. And if you look at the courses, no lecture a week from today either. So we won't have a quiz or homework due a week from today. So don't come up after class and say, are we going to have a quiz? We're not meeting on the 10th. We can miss one day out of the semester. All right, but I want to cover the projects a little bit today after we work that homework problem. Can I? Yes, I am capable of doing it.
May you please do number 1 for us?
We'll see. All right. So the one that was due today is homework 14.
You don't even know?
Nope, I have to look. You want me to do this one? It's so easy.
That really hurts.
It does? I'm thinking you might be victims of poor instruction by your professor.
Okay. I have post-traumatic stress syndrome, man. I got like stuff
From
like
my class.
But the freaking popo, man. I got stuff for no reason.
I can't hear the
I'm
word.
waiting.
You-
I got stuff.
Because you were wearing a shirt that was negative to the police. All right. Does anybody else want to see number 3 worked?
Yeah, I want to see number 2 and number 1.
And number 2. Matter of fact, do all the homework problems from the start of the year.
All right. Let's do one. I don't know. I'm kind of embarrassed to do this. Did it look like a hard circuit?
We're going through, I'll get to the point where I have my questions. It's kind of specific.
I just want reassurance on if I did it right. That's all.
Didn't we work these in class?
He says 5 seconds. I can't deal with the anxiety. Pain is high.
All right. So this was the first. So this is V-bias. Oh, and also next Wednesday, if you didn't notice, I was very clear before I forget so I don't have to announce it again in lab. We will not meet on April 10th, but you should start Lab 9 and the project, and here's when things are due. All right. All right, so these are the standard sizes. So what's the current flowing through here? And what's this DC voltage here?
Or no.
And if this is 5 volts, what's this voltage? So what's this DC voltage? What's the DC current flowing in the input source? I don't know, anything challenging there? All right. So what's this AC voltage here?
No,
Big
no, VSG is
capacitor.
negative EN.
The big capacitor there means that I'm shorting the AC to ground. So what's this AC voltage?
EN.
And what's VGS equal to?
Negative EN.
that because the difference between the two is 0 minus Vn?
Yeah,
Okay.
V gate minus V source. So far, so good. And then what's the AC current flowing in here? Or what? So what is that in this problem? This is 1 millivolt, I think. And, yeah, minus 1 millivolt. And then what is the AC current?
GM. Kept getting 155 with GM.
Okay.
So there's not an equal output resistance as well, it has to be calculated.
Well, we have to calculate V out, right?
Okay, so Vn is only, okay, so there's my question. So when we're calculating V out, then we actually see the respective output resistance. That's the part I didn't understand. There you go, okay, that's that. I didn't understand that.
So what's V out equal to?
ID times auto green parallel with R1.
Because it's going backwards, right? So it's minus, minus. Everybody follow that? Clayton, do you follow that?
No.
All right. So if I take a current source of 1 amp like this and I put it through a resistor of 1 ohm like this, won't the current like this be 1 amp? And won't the voltage here then be minus 1 volt? So if I do the same thing, my current I just calculate is minus 150. It would be minus 150 minus then times R out P and R out N because it's backwards. So it would be minus minus.
So then there's no, so then for V out, the other measurement at that node, we're not.
Oh no, I don't
Is this same, is this same? So then, going back to the other circuits before, where the source was on the gate, is it the same model? Use the same
Yeah.
DC model?
Yeah.
Okay, I don't understand that one either.
All right. So before I move on though, before got a lot of math on this. And this voltage goes up here. For AC, it's going up, right?
Mm-hmm.
What does it do qualitatively to the VGS here? Makes it smaller. So what happens to the current in that transistor?
Should go down.
Goes down. And if it goes down, this is a constant current. It's going to charge or make the output go up. So that's why I know the gain's positive. So why don't I do a common source, unless you don't want me to. Well, let's do number 1 then. So you were like working these homeworks and going, man, these are hard. And I was like, man, I'm giving them easy problems. See how out of touch with reality I am?
It's easy when you know what you're doing.
Yeah, it's always easier. All right, which one? This is the source follower. Do you want to do this one again? All right. Are you sure you guys are using my videos? Honestly. I'm having a hard time believing it.
I guess like just the biggest thing before I write it down, like I'm having a hard time making a connection between how to
do DC analysis, and then once you've done the DC, use the DC parameters to write the small signal parameters. Small signal parameters are the AC ones. So you do the DC calculations, and once you've done the DC, then you move to AC by calculating the small signal parameters. How was your 320 education?
Oh, I had a horrible teacher. Who doesn't?
Those 221 students keep asking me, you're going to teach 320, you're going to teach 320, and I'm like, no. All right, tell me how to find the gain of this one. Let's just do the AC part. What's VGS equal to? What's the current in that transistor equal to? And let's see, I'm going to redraw this, except now, let me draw it a little differently. So this is AC ground. What's the current that flows there, and what's the current that flows there? Any questions on that? So would you then agree that the current that goes into this node, which is GM times V in minus V out, is equal to the current that goes out of the node, which is V out over RON divided by 2? Does it bother you that I didn't write V out over R out N plus V out over R out N? Because I know two resistors of the same value in parallel are a half. And then there I can write, separating everything, GMVN equals V out times GM plus 2 over R out N. And V out over V in equals GM plus 2 over R out N over GM, or 1 plus 2 GM R out over 1. This term's going to be, well, what's GM R out again from the beginning of the semester? Open circuit gain. That's got to be big. So this will be about 0, and so that's equal to 1. Yes. What did I flip? Oh, all right, let's fix it. And then what was it when we derived for source follower? What did we say if you use this? The gain's almost approximately 1, but in real life, what is it that's used to calculate the gain? What limits the gain to get about 0.7 or whatever? Body effect. Okay, what about any questions on this? Does it look easy when I do it? No, it's not. No, it's not. It's the same. Drain to source, drain to source. Current flows from drain to source. Drain to source. For PMOS, it's complementary. CMOS, source to drain.
You look so excited.
Yeah, I got a lot going on. All right. I do like teaching though, man. Don't give me grief. Yes?
In one of your videos, I think you mentioned that you're going to go over the benefits and like about each amplifier
I have been. Remember the first one, common source, you get power gain, you get voltage gain and current gain. Source follower, you only get current gain, the voltage gain's near 1, and the input capacitance is very low. So we'd use the source follower for applications requiring small input capacitance. Then I gave an example, right? And then a common gate amplifier can be used where you're passing a current from like a photodetector to the output, and you're just basically amplifying the current directly without changing, or amplifying the current or changing the current into a voltage. That's very useful when your input has to stay at a constant potential, as in a photodiode application. Haven't I been going over those, or am I remembering it wrong? All right, let's do one more, common source. And then we'll do a PMOS, whatever. So we'll do this one. Yeah, let's put the big resistor in, the capacitor V in, and then I'm going to say, what is VGS here? VGS is always the gate voltage minus the source voltage. So what's the current that flows? And then this one's output resistance.
Parallel with.
Pull backwards. That homework was unreasonably hard.
Yeah.
All right. Let's do a PMOS on the homework, and then we'll get back, and we'll talk about projects, and we'll get back to frequency response. So which one of these, you want me to do a common gate, PMOS source follower, what, which one? Pick an amplifier, any amplifier.
Push-pull.
It's here. Which one do you want? This one? All right, let me sketch that. I got a question while I'm sketching it. If I remove or disconnect the input VS2, will the amplifier bias up correctly? And if so, why? And if not, why not? So if I remove V in, will the amplifier bias up correctly? The answer is yes. Really? Then where does the DC current flow? It's an open. If I remove that voltage source, there's no place for the DC current to flow. That was one of the things when I was learning digital. They didn't teach me in the lab. I'd be going, I'd like not connect anything to the input of a digital gate. So you're not grounding it. And then I'd be like, why isn't my circuit behaving right? Well, because you got to ground it to get a 0. Nothing there doesn't mean a 0, right? Especially back then when they were used TTL, not CMOS. And we finally stopped teaching TTL. And I'm like, it's been 20 years since anybody used TTL logic. We need to use CMOS. What's that? I know it still exists. It's just not something you should be spending a lot of time on. You shouldn't be designing new designs in LSI or SS, small scale integrated chips in TTL. That's ridiculous, actually. All right, well, what do I know?
Well, I thought VGTs were a little bit better for like analog.
They are.
They are like.
Yeah, but it's more expensive, and you got to integrate digital functionality. That's why most of the stuff we do in our group is by CMOS, bipolar chips in CMOS. All right, so let's write the voltages. What's V bias for? Same old sizes. And what is this voltage here, or what's the current flowing here then? That's why when you say this is hard, I'm like, are you kidding me? What's the DC voltage there? And what's this voltage? And what's this voltage, DC? All right. What's the AC voltage there? What's the AC voltage there? What?
Negative 1 million. Negative the other side.
If I write it like that? Anybody agree? So what's the current flowing in here?
Negative GM.
All right, let's ask, what's VSG?
Negative EM.
Am I going too slow? Yes. Looking good? And what is the V out then? This flows to ground. It's equal to this current flows like this. Righto. And that's times R out N in parallel with R out P. And so that would be V out over V in equals minus GM R out N in parallel with R out P. However, if you didn't ground the positive and you AC grounded the negative, it would be like this. And then it would be equal to positive GM R out N in parallel with R out P. What? Yeah, for your input. It's depending on how you connect the input. Looking good? Really, did you want me to go over the homework, or were you tweaking me? Just wanted me to burn some class time not talking about frequency response. It was helpful? I thought everything I did in class was helpful. Just ask me. All right, let's talk about the projects. I'm just going to give you a general overview in case you get bored this weekend and you want to work on your projects. So the first input stage, there's other topologies, but for a basic op amp, the input stage is a diff amp with a current mirror load. So here is a current mirror load. Looking good? Now I need a tail current down here, and what I'm going to do is I'm going to connect up, and I'm going to use all the same size devices. So I get twice the current. Of course, I could write it as 2 times W here, but I get twice the current flowing, and this will be my V bias 4 and my V bias 3. And the reason we use Cascode for current, or for a diff amp, is because of good common mode rejection ratio, which we'll talk about in a week or so when we talk about diff amps. Okay, so first question, input common mode range. So in an op amp, the 2 inputs are basically at the same voltage, right? In a real op amp, they're off by a little bit. If you have a gain of 1,000, they're going to be off by, say, a millivolt. But for all intents and purposes, for doing an analysis, you assume they're at the same potential. So they're common potential. In real life, they're not at exactly the same potential because it's not an ideal op amp, it's an op amp with finite gain. I remember like in 1988, I was working with a senior engineer from California. We were troubleshooting an op amp design, and I was going through and I said, oh, the op amps, this input's this and this input's this, and it was off a little bit. There's offsets and other issues. And the engineer says, no, they have to be at the same potential. That's not working. And I'm like, no, there's an offset, and the op amp has finite gain, especially a large or a high-speed one with lower gain. No, they have to. And so this guy was telling me they have to be at exactly. And I finally said to him, op amps aren't magic. All right? They don't have to be so magically, they don't have to be at the same potential. That was not how to win friends.
I mean, that means that V bias 3 and V bias 4 are sorted across the two transcoded?
Yeah. So this means V bias 3 is connected to these two transistors and V bias 4 is connected to those two. And you understand I drew it so they're drawn here and here, but I could put the connection here, in the middle of the connection here. I could also use two transistors instead of 4 with just twice the width. In modern, if you go out and get a job doing transistor level design in modern CMOS, they basically, especially in the smaller technology nodes, use one size transistor, and they use that transistor size over and over. So we need more drive. They put them in parallel like I'm doing here. Okay, there's reasons to do that for photolithography and the way they make the transistors. They're called FinFETs. Right, Mohammed? All right.
Oh, I see.
He's
So that's
stupid.
just really one wider.
He doesn't know I'm playing with my phone.
So that's really just one wider cascode. Gotcha.
Yeah, it's just a wider cascode. All right, so first one, minimum input common mode range. Or CMR. And why? What's common mode mean? It's the common input, that voltage that's the same on both. So what is the minimum voltage I can have on the input of this op amp if I use this diff amp? Need at least a VGS. Then if I've got wide swing cascodes, I need at least 2 VDS sat. So the minimum input common mode range is, or the input common mode range, or the minimum, we'll just say, is equal to VGS plus 2 VDS sat. In my op amp, if my input goes below that, then these transistors shut off. Everybody follow that? Yeah, you don't have enough to keep everything supported and up. So it's not magic. Remember, you have to keep a minimum input voltage. Now, there's ways that we'll talk about later in the semester where you can parallel PMOS and NMOS. So when the NMOS shut off, the PMOS are on. The NMOS and PMOS are both on. And then when the PMOS shut off, the NMOS are on. And then you can get an input common mode range that extends beyond the power supply rails. Okay, those are called wide swing op amps. Okay, so now what's the maximum input common mode range? So if I take these two voltages and I raise them up, I'm not going to have to worry about having enough voltage across those cascodes or across the VGS, right? However, what? I have the ones above, but more importantly, what? Well, hold on. You see that the current that flows through here is 2I, right? So then the current that flows through here is I, and the current that flows through here is I, and it's a current mirror. It's called a current mirror load. Everybody see that? So these, as you move these up, these transistors are going to continue sinking the 2I. They'll continue pulling it through here. So this node right here is going to be what? We just went over it a couple times already today. Everybody follow? This is my VSG. right? Now, don't these two transistors have the same VSG? Don't they have the same I? So won't they have the same drain to source or source to drain voltage? So what is the DC value here? This one's hard to follow. It's VDD minus VSG. Because of the symmetry. Same VSG, same I, then they've got to have the same drain to source voltage or source to drain voltage. So now I start to increase the inputs. These are fixed. This voltage is fixed at VDD minus VSG. But these guys, if I keep driving them up, they're going to triode. And they're going to triode, and if I go even higher, they're going to, when I say triode, what does that mean?
No longer separate.
They're going to
Still on, but they're not
they're going to look like
separate.
resistors.
Yeah.
They're going to look like resistors, and you're pulling the current through the resistors. These voltages will stay the same, but these will behave like resistors, and they won't amplify correctly. So I don't want these devices to triode. Does everybody get that? I want them to stay in saturation. So if I want this NMOS to stay in saturation, what equation do I use for that? VDS has to be greater than or equal to VGS minus V threshold N. Right? Same old thing. Or V drain has to be greater than or equal to V gate minus V threshold N because the sources cancel out. But what's the drain? And that's the gate, that's my input common mode range. That's minus V threshold N. So if I look at this, my maximum input common mode range is VDD minus VSG plus V threshold N. In this one, the maximum input voltage is just below VDD. But you see how, and there's tricks that we will do later that will actually get above VDD and below ground for input common mode range. You see, that's my input range. Now, you know everything about this DC-wise. You know what the maximum and minimum input common mode voltage is? Let's do one more before we talk about the next stage. What's the minimum VDD? And this is important for your projects because you have to design an op amp to run on 2 volts where your threshold voltages are 0.8 and 0.9. So what would be the minimum VDD that I would need here and why?
1 volt.
So this would be, what's the minimum voltage that I need here? Well, I don't know how I've selected the W and the L, so I'm going to leave it generic. VSG. Whatever VSG I pick. And in your designs, what VSG do you think you're going to pick? Something really close to the threshold voltage, because then your VDS sat and VSD sat's not very big. You're not going for super high speed. Okay, so I got that VSG. Here I am, I'm on top of the mountain and I'm hopping down. I hop down, I go down by VSG. What's the minimum voltage I need now? I need at least VDS sat. But again, if I pick VDS sat, which is slightly above the threshold voltage, this is going to be small, right? Or if I pick VGS and VSG that's slightly above the threshold voltage, this could be like 50 millivolts. So this will be 0.9 at least, but let's say 0.95 and say this is 0.05. So far we need at least 1 volt power supply. And then here, now I'm standing here, I've just hopped down. Now I need 2 VDS sat. So if I picked 850 millivolts for my VGS and 950 for my VSG, and I have 950 plus 50 plus 100, which would be 1.1 volts. So I could get something to operate down well below 2 volts at 1.1 volts. Everybody follow this. Say, we basically have gone over what's the minimum VDD, what's the input common mode range, what are all the voltages in the circuit. We're ready to go to our next stage. Before I do, any questions?
We also design a circuit which is basically figure 20.43.
Yeah. But I mean, if you use simpler bias voltage, you don't need to be as elaborate. Right? If you're only using 2 bias, V bias 3, V bias 4, you don't need all those other ones. We ready to move on? Any questions about this? So the next stage. So this right here, VDD minus VSG, that's at the same voltage as V bias 1. So I'm going to use that, and I'm going to come over here to a PMOS, same size, and I'm going to come down here. And this is going to be my output of my op amp. So you note, the current that I have flowing in here is what? And because I bias this up, current I have flowing in here is I, but there will be a little bit of an offset on the input of the op amp with the feedback in order to adjust that so that this current and this current are precisely equal. So I'm going to do an example here. If I have a gain here of 333, and then I have a gain here of 333, what's the gain of the op amp? Be 333 times 333, right? So well over 10,000. Okay, now I'm not telling you something. What happens when I put a resistive load here on the output? Remember, what's the typical output resistance of the transistor? R out in and R out P, which are? 4 and 5 meg, right? So if I put a 1K resistor here, what do you think happens to the gain on the output? It goes to way less than 1. And so then your overall gain isn't enough. So that's an issue we have to address later. But before I do, I want to do a quick example with this and show you the op amp operation. And then we'll put an output buffer on and do some other things. So what's roughly the minimum using our device sizes were available? What's the minimum that I can have my input common mode range? Yeah, it's roughly 1.05 plus 500, so about 1.65. What's the output swing? I didn't cover that. What's the range of the output? What can it go up to? No, the range, the voltage range of the output. VDD minus VSD sat. I don't want this transistor to triode. As soon as I go above VDD minus VSD sat, this transistor triodes. I need to have at least a VSD sat there. What can it go down to? 2 VDS sat. You see how by learning the way we did that we can then characterize everything in the op amp and know where the trade-offs are? Questions? Let's quickly show an example. Oh, and one other thing. If you're biased at 20 microamps, you put a 1K resistor here, what's the maximum current this op amp can source to the output? If I put a resistor here, where's the current? Source means what? Let me ask that. Supply. So the op amp can supply current and it comes from this PMOS, right? You don't supply current backwards through the NMOS, right? But you sink current from the NMOS. So what's the maximum current that I can sink here? What's it limited to? 20 microamps. Everybody follow that? Okay, so let's go put this in real quick. It won't take too long. Into LT Spice. And let's do this file, save as lecture 17. And then once we show this working, then what I'm going to do is I'm going to talk about the resistances and capacitances in the circuit, and we're going to talk about compensating the op amp. So I think we're going to need V bias 3 and V bias 4, and that's it. And then let's get out the scissors. And we don't need any of this stuff. But I don't want to spend time drafting, so let's move this out of the way. Not you. You're like, the projects scare me. No. And copy. And move. Oh, you know what? That was stupid. Why was it stupid? Because I need to put the lines in. I should have drawn that first. And then what else should I do while I'm here? And then let's grab one of these, plop it right here. Grab another one, Control E it. And then, actually, let's do this. Just like watching paint dry. Let's see. You're gonna need to tell me which one's the inverting or plus or minus and which one's the non-inverting. You know, op amp has an inverting input and a non-inverting input. I am. Just checking. Tell me if I'm making any mistakes. Are you sure? All right, so now if I move this terminal right here up, this voltage goes up. What does it do to the current in this transistor? Increases, right? And so what happens to this node right here? Gets pulled down. Then what happens to this transistor right here?
The current goes up.
The current goes up, but when you pull this, so this goes up, this goes down, that turns this on and causes the output to go up. So I'm gonna, did anybody not follow that? All right, let's do the other side so that you get something a little different. So this would be the plus, this would be the minus. So if I increase this voltage right here, what happens to this voltage right here? Goes down. What happens to the current that flows? Goes up. This is a current mirror. What happens to the current that flows in here? Goes up. So I got more current flowing. What does it do to this voltage? Pulls up. If it pulls up, what does it do to the current in this transistor? Shuts it off and allows the output to go down. So the minus causes the output to go down, the plus causes the output to go up. Exciting. Just out of curiosity, is there anybody that hasn't seen op amps before? Like used them in design, like non-inverting, inverting, that stuff? If anybody took 220 from me and said they didn't see op amps, I'd be like, what the hell? Carlos, you took 220 from me, didn't you? Oh. All right. That you're tweaking me. I thought you took 220 from me. All right, so let's go copy this. Oh, the students are loving the Laplace transforms. They're like, these are so cool and easy. I'm like, yep. 221. It's in the description. 221 covers Laplace transforms. All right, so here's my two op amps, or here's my op amp. I'm ready to use it. So what I'm going to do is I'm going to connect my output back to my minus and put it in the follower mode. So this is what I'm doing, just to make sure it's all clear. This one, I'm going to have an input going to the non-inverting, and I'm going to have a minus input going around like that. You're kidding me. This is like the simplest topology. So you put a little wiggle there, you get the same wiggle out. All right, well, let's find out. All right, and then I'm going to put a input here. And why don't I move this over? And because you like the time domain, we're going to put in a pulse going from, how about, let's not push it, let's go from 2 to 3 with a delay of, now we got to let the bias circuit start up. Let's do, how about 5 microseconds, a rise time of 10 microseconds, a fall time of 10 microseconds, and an on time of 100 microseconds. Then I'm going to simulate for, how about 150 microseconds. And let's move this over. So is it blowing anybody's mind that we have an op amp here? Okay, so now doing this part's easy. The hard part is compensating the op amp, and we're going to say that a lot. And what compensating means is making the op amp stable. Don't get OCD on me. What? No, I could hit click here, but you know. All right, so like I said, compensating is making the op amp stable. So let's hit run. And then let's look at the input. And we see a nice input. Now let's look at the output. The output looks good. All right, and let's actually, of course, there it is. This is nice and following, life is good. But of course, if you don't have any load to the op amp, then it's pointless, right? So here's what I'm going to do. I'm going to come over here, and I'm going to put a little capacitor on there. I'm not going to put a resistor because I know that's going to kill the gain. And I'm not going to put too big. I'll put 100 pico because that's what you have to use in your projects, right? The what? Yeah,
This is,
so this would be the load that you drive. So like load would be a speaker or a heating element or whatever, right? So now I hit save and then I hit run. And it still looks good. I don't want it to look that good. Let me highlight this net. Whoops. Huh. I don't want it to look good. Well, let's do one other thing real quick. Let's do VP minus V out. And if you look at that, do you see that the inputs are not precisely the same? Because the op amp has finite gain. Everybody see that? If they were precisely the same and it was an ideal op amp, it would be 0. But let's make the capacitor a little bit bigger, or put a resistance on here. Hit OK and hit run. And then let's plot VP again. And there's my V out. And it should be oscillating. I don't know why it's not, but tell me, why is it taking V out so long to go down? Capacitor's bigger, but if I wanted to if I wanted to write an equation and determine what the slope of that line is, what would I do? Yeah, so if I look, the capacitor is being discharged through this constant current source, right? So if I look at the slope, it'll be 1,000 pico, or it'd be 20 micro divided by 1,000 pico. So if I made the capacitor twice or half the size, you would see it go down twice as fast. So we can do that real quick. Go to 500. Hit run. And it went down twice as fast. All right. No, here. This is, you should remember this. So I equals C dV dt. If I put a capacitor here, the current that goes out I is 20 micro. The capacitance value is 500 pico. And that's the dV dt, which is the slope. I don't have that problem going up because if I yank this node down, this transistor turns on more and pulls it up. Okay? So let's do a couple more things here before I do. Any questions? Yes?
I'm still not sure I understand why there's the double I at the bottom.
The double what?
Where you got the double current at the bottom of the.
Do you mean here?
Yeah.
You don't like that?
I'm just not sure why.
Oh, because I want all the transistors to conduct the current I. So here, let's do this. Just to make sure it's not confusing too much, because it would have confused me when I was learning, is let's do the following. Boom like this. Boom like that. And you understand that when the transistors are connected like this in parallel, that I could just make one transistor of 20 by 2, one transistor of 20 by 2, and it'd be the same thing as well. So I get the same result. Okay, so now I wasn't planning on taking the whole lecture for this, but I think it's useful because I do want you to get going on your projects. Let's verify a few of these terms.
Why is the rise time much faster than the fall time?
I
understand the fall, I understand what's
Yeah,
going on.
remember, when you have the rise time, it's the PMOS. This node can get yanked down, right? It's not at a constant bias voltage like these are. So when I yank this node down, it turns this transistor on, and I'm not fixed at 20 microamps. I get more current that I can supply. Because I don't have a constant gate voltage. I'm yanking it down with the diff amp. All right, so let's do this. The first one we said is minimum input common mode voltage. Everybody follow that? So let's start with this pulse at 0, and we'll go to 3. And we said the minimum input common mode voltage is, what was it, 1.65? And what I'm going to do to verify that, we'll hit run, is you see it's off a little bit, but if you look, I'm going to plot instead the current flowing in this transistor. And you see that, and let's plot the input as well. If you look, the current goes to 20 microamps when the input gets to about 1.2 volts. I guess I was off on my estimate. It was 1.05 plus the 2 VDS sats, so it's a little bit lower than what I estimate. But do you see how the current is going to, well, no. If I go up here, it's pretty close. It gets to 20 microamps when the VP gets to 1.65. Anybody follow what we're looking at? Yeah, as soon as that input pulse gets above 1.65, as soon as the input pulse gets above 1.65, these turn on and the transistors start to conduct. Now, doing the positive side is a little bit more challenging because on the positive side, we have to look at when the gain drops, which is when these triode. So I'm going to go all the way up to 6 volts on the input, and you'll see the output can't go above 5, so you'll see it start before you get to 5, just fail. But now if I plot V in or VP and I plot V out, let's just plot VP and V out on the same plot. You see here that, okay, when I get up to my input voltage gets high enough, I start to follow. Then when I approach but you can see right here, you see how it's kind of rounding off? That's because the gain of the op-amp's dropping and it can't no longer follow the input. Okay, the feedback's not strong enough to follow the input, so it starts to get sloppy and round off. And that's pretty close to what we calculated, which was VDD minus VSD set. Or VDD minus VSG plus V threshold in. That's going to be like 4.7 volts or something like that. Everybody see that? What about output swing? You can see there also from the output swing what the op-amp can do. Let's do one more thing here. And then we're going to talk about the compensation in this particular topology. Let's talk about what happens or show what happens when you have a resistance. And I don't want to go crazy, but tell me what a resistor value we could use is. Could I use 1K?
No.
No, that's way too small. But if I look at like 100K, 100K is way smaller. I'll be able to see the effects of finite gain there because that's 100K means it's going to kill the gain from 2.2 meg. Does everybody see that? So the effective resistance I have here is 4 meg in parallel with the R out cascode, or 4 meg. So I put 100K there. We go from 4 meg or 4,000K to 100K. So it's 40 times smaller. We'll see 40 times smaller gain. So let's plop that down. Let's hit run. And I don't know if you can see it very pronounced. Let's go. So that was a factor of 20 decrease in gain. Let's go a factor of 200 decrease in gain and see what you can get. Can you tell there? How?
V out went down.
Yeah, V out's only getting up to slightly below 4.2. But using that 1K it discharge or 10K discharges that capacitor a lot quicker because now it has not only the op amp but the resistor pulling the charge off the capacitor. Everybody see this? All right, let's go look now real quick at the topology again. And then we'll have our grade booster. We want you to feel alive. So here is the topology for the op amp. I'll just put a current source like that. I'm gonna be lazy. Then I'm gonna come over here and I'm gonna put my nice little PMOS common source. And I'll put another current source down here, 2I. And then here's my output, V out. Here was V positive, here was V minus. Note, when I write these, I don't use plus and minus generally when I do the simulations. Because in the olden days, you couldn't use special characters, so I don't use those. It's like when you are a programmer, you get used to not using multi or spaces in a programming name, right? Because their syntax can get messed up. It has to be a continuous line of characters, unless you define it different like that.
One of them without connected?
Yeah. All right, and so now, if I ask you, what is the effective resistance on this node? I'm going to call that resistance R1, and I'm going to call this node 1. What is the effective resistance on this node? Well, does the gate load the node with resistance? No, it's a piece of polysilicon over glass. So what loads the node? R out P and R out N. Everybody see that?
Why are we not taking into account the cascode of the source?
Here?
Yeah.
Because you can show that when these go in opposite directions, which they will, this essentially stays at ground potential. So it's just R out in. We'll cover this more later. Then if I put a resistor here and I call the output node 2, what is R2? And parallel with R out cascode, and if it's there. Everybody got that? Now here I've got a capacitor I'm going to call C1 associated with node 1, and here I've got a capacitor C2 associated with C2 or node 2. And so on node 1 I've got a CSG here. Then I've got a CSG here. And then what we're going to do, and we'll pause on that, I'll come back to that. Then here I have a capacitance of I said that wrong. CDG, or no, this is CSG. So CSG, and then I've got a C drain to gate here. And then I've got a capacitance here, which I'll call C gate to drain. And so the C1, and I'm not going to take the time, is this capacitor is this one plus this one plus this one. C2 would be this capacitor here, which I'm going to break up a little bit in parallel with the capacitance I had here in the source. The whole point and what I'm getting at is the following. When we, which is what I was hoping to cover today, but I got off on the working problem so you actually know what's going on thing. Don't you hate it when professors do that? Isn't it what? No, it's the professor goes off on a tangent and starts working problems for you.
Homework to ask questions about, we wanted to take that last time.
What? You don't want me to assign homework? What a surprise. Okay. So you see this resistor here, R1? That's the output resistance of the diff amp. This is the capacitance on the resistance on the node 1 of the diff amp. There's node 1. Here's node 2. Node 2 is the output. And in node 2, I've got the R2 that's there, and then the GMV1, which is the current source. Now I'm going to skip ahead a little bit. This is the circuit I analyzed here in this pole splitting summary. If I go now to chapter 24, and I look at the op amps in that chapter, specifically, let's look at just a basic op amp right here from our long channel. That look familiar? Except this is short channel, sorry. This is 100 by 2, these are 50 by 2. And then we've got this compensation network here, this diff amps. And if I go back over now and I read this, I get R1 is R out in parallel with R out 2, R2 is R out P in parallel. Doesn't this look familiar? It's what we just went over. GM1 equals GMN is 150, GM2 is GMP, the C1, C2. Then I can plug in the equations and get the frequency response. So this is what I'd like you to do with, I think, did you do some of that today in today's homework, or is that next week's? So next week you'll have to do that, where you're plugging in the numbers and calculating the frequency and then comparing it to simulations, okay? So read through that. I'll change the web so that it doesn't show that we covered pole splitting today, but I'll say discuss projects and frequency response or something like that. And then you should have enough homework, keep you busy, and the projects. Any last second questions? Does the project seem more doable now? Come on. No, I didn't. All right. Now, if you can get that op amp topology to meet the specs, I want to see.